Stanford University.
Okay, so good afternoon, everyone. Let's get started. Hi, so for those of you who I haven't met yet, my name is Serena Young, and I'm the third and final instructor for this class. And I'm also a PhD student in Feifei's group. Okay, so today we're going to talk about backpropagation and neural networks. And so now we're really starting to get to some of the core material in this class. Before we begin, let's see. So a few administrative details. So assignment 1 is due Thursday, April 20th. So reminder, we shifted the date back by a little bit. And it's going to be due 11:59 p.m. on Canvas. So you should start thinking about your projects. There are TA specialties listed on the Piazza website. So if you have questions about a specific project topic you're thinking about, you can go and try and find the TAs that might be most relevant. And then also for Google Cloud, so all students are going to get $100 in credits to use for Google Cloud for their assignments and project. So you should be receiving an email for that this week. I think a lot of you may have already, and then for those of you who haven't, they're going to come, should be by the end of this week. Okay, so where we are, so far we've talked about how to define a classifier using a function f parameterized by weights w. And this function f is going to take data x as input and output a score of a vector of scores for each of the classes that you want to classify. And so from here we can also define a loss function. So for example, the SVM loss function that we've talked about, which basically quantifies how happy or unhappy we are with the scores that we've produced, right? And then we can use that to define a total loss term. So L here, which is a combination of this data term combined with a regularization term that expresses how simple our model is. And we have a preference for simpler models for better generalization. And so now we want to find the parameters W that correspond to our lowest loss, right? We want to minimize the loss function. And so to do that, we want to find the gradient of L with respect to W. So last lecture, we talked about how we can do this using optimization, where we want to iteratively take steps in the direction of steepest descent, which is the negative of the gradient, in order to walk down this loss landscape and get to the point of lowest loss, right? And we saw how this gradient descent can basically take this trajectory looking like this image on the right, getting to the bottom of your loss landscape. Okay, and so we also talked about different ways for computing the gradient, right? We can compute this numerically using finite difference approximation, which is slow and approximate, but at the same time, it's really easy to write out. You know, you can always get the gradient this way. We also talked about how to use the analytic gradient, right? And computing this it's fast and exact once you've gotten the expression for the analytic gradient. But at the same time, you have to do all the math and the calculus to derive this. So it's also easy to make mistakes, right? So in practice, what we want to do is we want to derive the analytic gradient and use this. But at the same time, check our implementation using the numerical gradient to make sure that we've gotten all of our math right. So today we're going to talk about how to compute the analytic gradient for arbitrarily complex functions using a framework that I'm going to call computational graphs. And so basically what a computational graph is that we can use this kind of graph in order to represent any function where the nodes of the graph are steps of computation that we go through. So for example, in this example of a linear classifier that we've talked about, the inputs here are x and w, right? And then this multiplication node represents the matrix multiplier, the multiplication of the parameters w with our data x that we have, outputting our vector of scores. And then we have another computational node, which represents our hinge loss, right? Computing our data loss term, li. And we also have this regularization term at the bottom, right? So this node which computes our regularization term. And then our total loss here at the end L is the sum of the regularization term and the data term. And the advantage is that once we can express a function using a computational graph, then we can use a technique that we call backpropagation, which is going to recursively use the chain rule in order to compute the gradient with respect to every variable in the computational graph. And so we're going to see how this is done. And this becomes very useful when we start working with really complex functions. So for example, convolutional neural networks that we're going to talk about later in this class. We have here the input, right, image at the top. We have our loss at the bottom. And the input has to go through many layers of transformations in order to get all the way down to the loss function. And this can get even crazier with things like like a neural Turing machine, which is another kind of deep learning model. And in this case, you can see that the computational graph for this is really insane. And especially, we end up unrolling this over time. It's basically completely impractical if you want to compute the gradients for any of these intermediate variables. OK, so how does backpropagation work? So we're going to start off with a simple example, where again, our goal is that we have a function. So in this case, f of x, y, z equals x plus y times z. And we want to find the gradients of the output of the function with respect to any of the variables. So the first step always is we want to take our function f, and we want to represent it using a computational graph. Right, so here our computational graph is on the right. And you can see that we have our first, we have the plus node, so x plus y, and then we have this multiplication node, right, for the second computation that we're doing. And then now we're going to do a forward pass through this network. So given the values of the variables that we have, so here x equals -2, y equals 5, and z equals -4, I'm going to fill these all in our computational graph. And then here we can compute an intermediate value. So x plus y gives 3. And then finally, we pass it through again through the last node, the multiplication, to get our final node of f equals -12. So here, we want to give every intermediate variable a name. Right? So here I've called this intermediate variable after the plus node q. And we have q equals x plus y. And then f equals q times z using this intermediate node. And I've also written out here the gradients of q with respect to x and y, which are just 1 because of the addition. And then the gradients of f with respect to q and z, which is z and q respectively because of the multiplication rule. And so what we want to find is we want to find the gradients of f with respect to x, y, and z. So what backprop is, it's a recursive application of the chain rule. So we're going to start at the very end of the computational graph, and then we're going to work our way backwards and compute all of the gradients along the way. So here, if we start at the very end, right, we want to compute the gradient of the output with respect to the last variable, which is just f. And so this gradient is just 1. It's trivial. So now moving backwards, we want the gradient with respect to z, right? And we know that df over dz is equal to q. So the value of q is just 3. And so we have here df over dz equals 3. And so next, if we want to do df over dq, what is the value of that? What is df over dq? So we have here df over dq is equal to z, right? And the value of z is -4. So here we have df over dq is equal to -4. OK, so now continuing to move backwards through the graph, we want to find df over dy. Right? But here, in this case, the gradient with respect to y is not connected directly to f. Right? It's connected through an intermediate node of z. And so the way we're going to do this is we can leverage the chain rule, which says that df over dy can be written as df over dq times dq over dy. And so the intuition of this is that in order to get to find the effect of y on f, this is actually equivalent to if we take the effect of q times q on f, which we already know, right? df over dq is equal to -4, and we compound it with the effect of y on q, dq over dy. So what's dq over dy equal to in this case? 1. Right, exactly. So dq over dy is equal to 1, which means if we change y by a little bit, Q is going to change by approximately the same amount, right? This is the effect. And so what this is doing is this is saying, well, if I change y by a little bit, the effect of dq, effect of y on q is going to be 1, and then the effect of q on f is going to be approximately a factor of -4, right? So then we multiply these together, and we get that the effect of y on f is going to be -4. Okay, so now if we want to do the same thing for the gradient with respect to x, right, we can follow the same procedure. And so what is this going to be? Heard the same? Yeah, exactly. So in this case, we want to again apply the chain rule, right? We know the effect of q on f gradient is -4, and here again, since we have also the same addition node, dq over dx is equal to 1. Again, we have -4 times 1, right? And the gradient with respect to x is going to be -4. Okay, so what we're doing in backprop is we basically have all of these nodes in our computational graph, but each node is only aware of its immediate surroundings, right? So we have, at each node, we have the local inputs that are connected to this node, the values that are flowing into the node, and then we also have the output that is directly outputted from this node, right? So here, our local inputs are x and y, and the output is z. And at this node, we also know the local gradient, right? We can compute the gradient of z with respect to x and the gradient of z with respect to y. And these are usually really simple operations, right? Each node is going to be something like the addition or the multiplication that we had in that earlier example, which is something where we can just write down the gradient and we don't have to go through very complex calculus in order to find this. Yeah, so basically, if we go back, So if we go back here, we could exactly find all of these using just calculus. So we could say, we want df over dx, right? And we can probably expand out this expression and see that it's just going to be z. But we can do this in this case because it's simple. But we'll see examples later on where once this becomes a really complicated expression, you don't want to have to use calculus to derive, right, the gradient for a super complicated expression. And instead, if you use this formalism and you break it down into these computational nodes, then you can only ever work with gradients of very simple computations, right? At the level of additions, multiplications, exponentials, things as simple as you want them. And then you just use the chain rule to multiply all of these together and get the value of your gradient without having to ever derive the entire expression. Does that make sense? Okay, so we'll see an example of this later. And so, was there another question? Yeah. Negative. Okay, yeah. So the -4. These were the green values on top were all the values of the function as we passed it forward through the computational graph, right? So we set up here that x is equal to -2, y is equal to 5, and z equals -4. So we filled in all of these values, and then we just wanted to compute the value of this function, right? So we said this value of q is going to be x plus y. It's going to be -2 plus 5, and it's going to be 3. And we have z is equal to -4. So we fill that in here, and then we multiplied q and z together, -4 times 3, in order to get the final value of f, right? And then the red values underneath were as we were filling in the gradients as we were working backwards. Okay. Okay, so right, so we said that we have these nodes, and each node basically gets its local inputs coming in and the output that it sees directly passing on to the next node. And then we also have these local gradients that we computed, right? The gradient of the immediate output of the node with respect to the inputs coming in. And so what happens during backprop is we have these we start from the back of the graph, right? And then we work our way from the end all the way back to the beginning. And when we reach each node, at each node, we have the upstream gradients coming back, right, with respect to the immediate output of the node. So by the time we reach this node in backprop, we've already computed the gradient of our final loss L with respect to Z, right? And so now what we want to find next is we want to find the gradients with respect to just before the node, to the values of x and y. And so as we saw earlier, we do this using the chain rule, right? We have from the chain rule that the gradient of this loss function with respect to x is going to be the gradient with respect to z times compounded by this gradient, local gradient of z with respect to x, right? So in the chain rule, we always take this upstream gradient coming down and we multiply it by the local gradient in order to get the gradient with respect to the input. So the question is whether this only works because we're working with the current values of the function. And so it works, right, given the current values of the function that we plug in, but we can write an expression for this still in terms of the variables, right? So we'll see that gradient of L with respect to z is going to be some expression, and gradient of z with respect to x is going to be another expression, right? But we plug in these, we plug in the values of these numbers at the time in order to get the value of the gradient with respect to x. So what you could do is you could recursively plug in all of these expressions, right? Gradient with respect z with respect to x is going to be a simple expression, right? So in this case, if we have a multiplication node, gradient of z with respect to x is just going to be y, right? We know that. But the gradient of L with respect to z, this is probably a complex part of the graph in itself, right? So here's where we want to just, in this case, have this numerical, right? So as you said, basically this is going to be just a number coming down, right, of value, and then we just multiply it with the expression that we have for the local gradient. And I think this will be more clear when we go through a more complicated example in a few slides. Okay, so now the gradient of L with respect to y, we have exactly the same idea, where again we use the chain rule. We have gradient of L with respect to z times the gradient of z with respect to y, right? We use the chain rule, multiply these together, and get our gradient. And then once we have these, we'll pass these on to the node directly before, connected to this node. And so the main thing to take away from this is that at each node, we just want to have our local gradient that we compute, just keep track of this. And then during backprop, as we're receiving numerical values of gradients coming from upstream, we just take what that is, multiply it by the local gradient, and then this is what we then send back to the connected nodes, the next nodes going backwards without having to care about anything else besides these immediate surroundings. So now we're going to go through another example, this time a little bit more complex, so we can see more why backprop is so useful. So in this case, our function is f of w and x, which is equal to 1 over 1 plus e to the negative of w0 times x0 plus w1 x1 plus w2. Right, so again, the first step always is we want to write this out as a computational graph. So in this case, we can see that in this graph, right, first we multiply together the w and x terms that we have, w0 with x0, w1 with x1, and w2. Then we add all of these together, right? Then we scale it by -1. We take the exponential, we add 1, and then finally we do 1 over this whole term. And then here I've also filled in values of these. So let's say given values that we have for the w's and x's, right, we can make a forward pass and basically compute what the value is at every stage of the computation. And here I've also written down here at the bottom the values, the expressions for some derivatives that are going to be helpful later on. So same as we did before with the simple example. Okay, so now when we're going to do backprop through here, right? So again, we're going to start at the very end of the graph. And so here again, the gradient of the output with respect to the last variable is just 1. It's just trivial. And so now moving backwards one step, right? So what's the gradient with respect to the input just before 1 over x? Well, so in this case, we know that the upstream gradient that we have coming down, right, is this red 1. Right? This is the upstream gradient that we have flowing down. And then now we need to find the local gradient. Right? And the local gradient of this node is 1 over x. Right? So we have f of x equals 1 over x here in red. And the local gradient of this, df over dx, is equal to negative 1 over x squared. Right? So here we're going to take negative 1 over x squared and plug in the value of x that we had during this forward pass, 1.37. And so our final gradient with respect to this variable is going to be negative 1 over 1.37 squared times 1 equals negative 0.53. Right? So moving back to the next node, we're going to go through the exact same process. Right? So here, the gradient flowing from upstream is going to be negative 0.53. Right? And here, the local gradient, the node here is a plus 1. And so now looking at our reference of derivatives at the bottom, we have that for a constant plus x, the local gradient is just 1. Right? So what's the gradient with respect to this variable using the chain rule? So it's going to be the upstream gradient of negative 0.53 times our local gradient of 1, which is equal to negative 0.53. So let's keep moving backwards one more step. So here we have the exponential, right? So what's the upstream gradient coming down? Right, so the upstream gradient is negative 0.53. What's the local gradient here? It's going to be the local gradient of e to the x, right? This is an exponential node. And so our chain rule is going to tell us that our gradient is going to be negative 0.53 times e to the power of x, which in this case is negative 1 from our forward pass. And this is going to give us our final gradient of negative 0.2. OK, so now one more node here. The next node that we reach is going to be a multiplication with negative 1. Right, so here, what's the upstream gradient coming down? Negative 0.2, right. And what's going to be the local gradient? You can look at the reference sheet. It's going to be, what was it? I think I heard it. It's going to be minus 1, exactly. Yeah, because our local gradient says it's going to be df over dx is a, right? And the value of a that we scaled x by is negative 1 here. So we have here that the gradient is negative 1 times negative 0.2, and so our gradient is 0.2. OK, so now we've reached an addition node. And so in this case, we have these two branches both connected to it, right? So what's the upstream gradient here? It's going to be 0.2, right, just as everything else. Here now the gradient with respect to each of these branches, it's an addition, right? And we saw from before in our simple example that when we have an addition node, the gradient with respect to each of the inputs to the addition is just going to be 1. Right, so here our local gradient for our looking at our top stream is going to be 1 times the upstream gradient of 0.2, which is going to give a total gradient of 0.2. Right, and then for our bottom branch, we do the same thing. Right, our upstream gradient is 0.2, our local gradient is 1 again, and the total gradient is 0.2. So is everything clear about this? OK. So we have a few more gradients to fill out. So moving back, now we've reached W0 and X0. And so here we have a multiplication node, right? So we saw the multiplication node from before. It just the gradient with respect to one of the inputs just is the value of the other input. And so in this case, what's the gradient with respect to W0? I'm hearing minus 0.2, exactly. Yeah, so with respect to W0, we have our upstream gradient 0.2, right, times our, this is the bottom one, times our value of x, which is -1, we get -0.2. And we can do the same thing for gradient with respect to x0. It's going to be 0.2 times the value of W0, which is 2, and we get 0.4. Okay, so here we've filled out most of these gradients. And so there was a question earlier about why this is simpler than just deriving the analytic gradient, the expression with respect to any of these variables, right? And so you can see here, all we ever dealt with was expressions for local gradients that we had to write out. So once we had these expressions for local gradients, all we did was plug in the values for each of these that we have and use the chain rule to numerically multiply this all the way backwards and get the gradients with respect to all of the variables. And so we can also fill out the gradients with respect to W1 and X1 here in exactly the same way. And so one thing that I want to note is that, right, when we're creating these computational graphs, we can define the computational nodes at any granularity that we want to. So in this case, we broke it down into the absolute simplest that we could, right? We broke it down into additions and multiplications. It basically can't get any simpler than that. But in practice, right, we can group some of these nodes together into more complex nodes if we want, as long as we're able to write down the local gradient for that node, right? And so as an example, if we look at a sigmoid function, so I've defined the sigmoid function in the upper right here, of a sigmoid of x is equal to 1 over 1 plus e to the negative x. And this is something that's a really common function that you'll see a lot in the rest of this class. And we can compute the gradient for this. We can write it out, and if we do actually go through the math of doing this analytically, we can get a nice expression at the end. So in this case, it's equal to 1 minus sigma of x, so the output of this function, times sigma of x, right? And so in cases where we have something like this, we could just take all the computations that we had in our graph that made up this sigmoid, and we could just replace it with one big node that's a sigmoid, right? Because we do know the local gradient for this gate. It's this expression d of the sigmoid of x over dx, right? So basically the important thing here is that you can group any nodes that you want to make any sorts of a little bit more complex nodes, as long as you can write down the local gradient for this. And so all this is basically a trade-off between how much math that you want to do in order to get a more kind of concise and simpler graph, right? Versus how simple you want each of your gradients to be, right? And then you can write out as complex of a computational graph that you want. Yeah, question? So they could also be connected into a single addition node. So the question was, is there a reason why W0 and X0 are not connected with W2? All of these additions just connected together. And yeah, so the answer is that you can do that if you want. And in practice, maybe you would actually want to do that because this is still a very simple node, right? So in this case, I just wrote this out into as simple as possible, where each node only had up to 2 inputs. But yeah, you could definitely do that. Any other questions about this? Okay, so the one thing that I really like about thinking about this like a computational graph is that I feel very comforted, right? Like anytime I have to take a gradient, find gradients of something, even if the expression that I want to compute gradients of is really hairy and really scary, whether it's something like the sigmoid or something worse, I know that I could derive this if I want to, but really, if I just sit down and write it out in terms of a computational graph, I can go as simple as I need to always be able to apply backprop and the chain rule and be able to compute all the gradients that I need, And so this is something that you guys should think about when you're doing your homeworks. As basically, anytime you're having trouble finding gradients of something, just think about it as a computational graph, break it down into all of these parts, and then use the chain rule. Okay, and so so we talked about how we could group these set of nodes together into a sigmoid gate. And just to confirm that this is actually exactly equivalent, we can plug this in, right? So we have that our input here to the sigmoid gate is going to be 1 in green. And then we have that the output is going to be here 0.73, right? And this will work out if you plug it into the sigmoid function. And so now if we want to do, if we want to take the gradient and we want to treat this entire sigmoid as one node, now what we should do is we need to use this local gradient that we've derived up here, right? 1 minus sigmoid of x times the sigmoid of x. So if we plug this in, and here we know that the value of sigmoid of x was 0.73. So if we plug this value in, we'll see that the value of this gradient is equal to 0.2. Right, and so the value of this local gradient is 0.2. We multiply it by the upstream gradient, which is 1. And we're going to get out exactly the same value of the gradient with respect to before the sigmoid gate as if we broke it down into all of the smaller computations. Okay, and so as we're looking at what's happening, right, as we're taking these gradients going backwards through our computational graph, there's some patterns that you'll notice where there's some intuitive interpretation that we can give these, right? So we saw that the add gate is a gradient distributor, right? When we pass through this addition gate here, which had 2 branches coming out of it, it took the gradient, the upstream gradient, and it just distributed it, passed the exact same thing to both of the branches that were connected. So here's a couple more that we can think about. So what's a max gate look like? So we have a max gate here at the bottom, right, where the inputs coming in are z and w. Z has a value of 2, w has a value of -1, and then we took the max of this, which is 2, right, and so we pass this down into the remainder of our computational graph. So now if we're taking the gradients with respect to this, the upstream gradient is, let's say, 2 coming back, right? And what does this local gradient look like? Yes. Right. Exactly. So the answer that was given is that z will have a gradient of 2, w will have the value gradient of 0. And so one of these is going to get the full value of the gradient just passed back and routed to that variable, and then the other one will have a gradient of 0. And so we can think of this as kind of a gradient router, right? So whereas the addition node passed back the same gradient to both branches coming in, the max gate will just take the gradient and route it to one of the branches. And this makes sense because if we look at our forward pass, what's happening is that only the value that was the maximum got passed down to the rest of the computational graph, right? So it's the only value that actually affected our function computation at the end. And so it makes sense that when we're passing our gradients back, we just want to adjust what, flow it through that branch of the computation. Okay, and so another one, what's a multiplication gate, which we saw earlier? Is there any interpretation of this? Okay, so the answer that was given is that the local gradient is basically just the value of the other variable. Yeah, so that's exactly right. So we can think of this as a gradient switcher, right? A switcher and I guess a scaler, where we take the upstream gradient and we scale it by the value of the other branch. Okay, and so one other thing to note is that when we have a place where one node is connected to multiple nodes, the gradients add up at this node, right? So at these branches, using the multivariate chain rule, we're just going to take the value of the upstream gradient coming back from each of these nodes, and we'll add these together to get the total upstream gradient that's flowing back into this node. And you can see this from the multivariate chain rule. And also thinking about this, you can think about this, that if you're going to change this node a little bit, it's going to affect both of these connected nodes in the forward pass, right? When you're making your forward pass through the graph. And so then when you're doing backprop, right, then now the both of these gradients coming back are going to affect this node, right? And so that's why we're going to sum these up to be the total upstream gradient flowing back into this node. Okay, so any questions about backprop going through these forward and backward passes? Right, so the question is, we haven't done anything yet to update the values of these weights. We've only found the gradients with respect to the variables. That's exactly right. So what we've talked about so far in this lecture is how to compute gradients with respect to any variables in our function, right? And then once we have these, we can just apply everything we learned in the optimization lecture, last lecture, right? So given the gradient, we now take a step in the direction of the gradient in order to update our parameters, right? So we can just take this entire framework that we learned about last lecture for optimization, and what we've done here is just learn how to compute the gradients we need for arbitrarily complex functions, right? And so this is going to be useful when we talk about complex functions like neural networks later on. Yeah. Yeah, so I can write this maybe on the board. Right, so basically if we're going to have, let's see, if we want to have the gradient of f with respect to some variable x, right, and let's say it's connected through variables, let's see, I, we can basically right, so this is basically saying that if x is connected to these multiple elements, right, let's say in this case different QIs, then the chain rule is taking all, it's going to take the effect of each of these intermediate variables, right, on our final output f, and then compound each one with the local effect of our variable x on that intermediate value. Right, so yeah, it's basically just summing all these up together. Okay, so now that we've done all these examples in the scalar case, we're going to look at what happens when we have vectors. Right, so now for variables x, y, and z, instead of just being numbers, we have vectors for these. And so everything stays exactly the same, the entire flow. The only difference is that now our gradients are going to be Jacobian matrices, right? So, so these are now going to be matrices containing the derivative of each element of, for example, z with respect to each element of x. Okay, and so to so give an example of something where this is happening, right? Let's say that we have our input is going to now be a vector. So let's say we have a 4096 dimensional input vector, and this is kind of a common size that you might see in convolutional neural networks later on. And our node is going to be an element-wise maximum, right? So we have f of x is equal to the maximum of x compared with 0 element-wise. And then our output is going to be also a 4096 dimensional vector. Okay, so in this case, what's the size of our Jacobian matrix? Remember I said earlier the Jacobian matrix is going to be, like each row it's going to be partial derivatives, a matrix of partial derivatives of each dimension of the output with respect to each dimension of the input. Okay, so the answer I heard was 4096 squared, and that's correct. So this is pretty large, right? 4096 by 4096. And in practice, this is going to be even larger because we're going to work with mini batches of, for example, 100 inputs at the same time, right? And we'll put all of these through our node at the same time to be more efficient. And so this is going to scale this by 100, and in practice, our Jacobian is actually going to turn out to be something like 400, and 9,000 by 409,000, right? So this is really huge and basically completely impractical to work with. So in practice, though, we don't actually need to compute this huge Jacobian most of the time. And so why is that? Like, what does this Jacobian matrix look like? If we think about what's happening here, where we're taking this element-wise maximum, and we think about what are each of the partial derivatives, right? Which dimension of the inputs affect which dimensions of the output? What sort of structure can we see in our Jacobian matrix? Okay, so I heard that it's diagonal. Right, exactly. So because this is element-wise, right, each element of the input, say the first dimension, only affects that corresponding element in the output, right? And so because of that, our Jacobian matrix, which is just going to be a diagonal matrix, right? And so in practice, then, we don't actually have to write out and formulate this entire Jacobian. We can just know the effect of x on the output, right? And then we can just use these values, right, and fill it in as we're computing the gradient. Okay, so now we're going to go through a more concrete vectorized example of a computational graph, right? So let's look at a case where we have the function f of x and w is equal to basically the L2 of w multiplied by x. And so in this case, we're going to say x is n-dimensional and w is n by n. Right, so again, our first step, writing out the computational graph. Right, we have w multiplied by x, and then followed by, I'm just going to call this L2. And so now let's also fill out some values for this. So we can see that, let's say have w be this 2 by 2 matrix, and x is going to be this two-dimensional vector. Right, and so we can say, label again our intermediate nodes. Our intermediate node after the multiplication is going to be q. We have q equals w times x, which we can write out element-wise this way. Right, the first element is just w11 times x1 plus w12 times x2, and so on. And then we can now express f in relation to q. Right, so looking at the second node, we have f of q is equal to the L2 norm of q, which is equal to q1 squared plus q2 squared. Okay, so we fill this in, right? We get q, and then we get our final output. Okay, so now let's do backprop through this, right? So again, this is always the first step. We have the gradient with respect to our output is just 1, right? Okay, so now let's move back one node. So now we want to find the gradient with respect to q, right? Our intermediate variable before the L2. And so q is a two-dimensional vector. And what we want to do is we want to find how each element of q affects our final value of f, right? And so if we look at this expression that we've written out for f here at the bottom, we can see that the gradient of f with respect to a specific qi, let's say q1, is just going to be 2 times qi, right? This is just taking this derivative here. And so we have this expression with respect to each element of qi. We could also, write this out in vector form if we want to. It's just going to be 2 times our vector of q, right, if we want to write this out in vector form. And so what we get is that our gradient is 0.44 and 0.52, this vector, right? And so you can see that it just took q and it scaled it by 2, right? Each element is just multiplied by 2. So the gradient of a vector is always going to be the same size as the original vector, and each element of this gradient is going to, it means how much this particular element affects our final output of the function. Okay, so now let's move one step backwards, right? What's the gradient with respect to w? And so here again, we want to use the same concept of trying to apply the chain rule, right? So we want to compute our local gradient of q with respect to w. And so let's look at this again element-wise. And if we do that, let's see what's the effect of each Q, right, each element of Q with respect to each element of W, right? So this is kind of the Jacobian that we talked about earlier. And if we look at this in this multiplication, Q is equal to W times X, right? What's the derivative or the gradient of the first element of Q, so our first element up top, with respect to W11. So Q1 with respect to W11. What's that value? X1, exactly. Yeah, so we know that this is X1, and we can write this out more generally of the gradient of Qk with respect to of Wij is equal to Xj. Right, and then now if we want to find the gradient with respect to of f with respect to each Wij, so looking at these derivatives now, we can use this chain rule that we talked to earlier, where we basically compound df over dqk for each element of q with dqk over Wij for each element of Wij, right? So we find the effect of each element of W on each element of Q and sum this across all Q. And so if you write this out, this is going to give this expression of 2 times Qi times Xj. Okay, and so filling this out, then we get this, this gradient with respect to W. And so again, we can compute this each element wise, or we can also look at this expression that we've derived and write it out in vectorized form. Right, so, okay, and remember, the important thing is always to check the gradient with respect to a variable should have the same shape as the variable. And so this is something really useful in practice to sanity check, right? Like once you've computed what your gradient should be, check that this is the same shape as your variable. Because again, the element, each element of your gradient is quantifying how much that element is contributing to your, affecting your final output. Yeah. The bold size, the bold size 1 is an indicator function. So this is saying that it's just 1 if k equals I. Okay, so let's see, so we've done that. And so now just, let's see, one more example. Now our last thing we need to find is the gradient with respect to Qi. So here, if we compute the partial derivatives, we can see that dqk over dxi is equal to wki, right? Using the same way as we did it for w, and then again we can just use the chain rule and get the total expression for that. Right, and so this is going to be the gradient with respect to x, again, of the same shape as x, and we can also write this out in vectorized form if we want. Okay, so any questions about this? Yeah. So we are computing the Jacobian. So let me go back here. Right, so if we're doing, so we have these partial derivatives of qk with respect to xi, right? And these are forming your the entries of your Jacobian, right? And so in practice, what we're going to do is we basically take that, and you're going to see it up there in the chain rule. So the vectorized expression of gradient with respect to x, right? This is going to have the Jacobian here, which is this transposed value here. So you can write it out in vectorized form. So in this case, the matrix is going to be the same size as W, right? So it's not actually a large matrix in this case, right? Okay, so the way that we've been thinking about this is like a really modularized implementation, right? Where in our computational graph, right, we look at each node locally and we compute the local gradients and chain them with the upstream gradients coming down. And so you can think of this as basically a forward and a backwards API, right? In the forward pass, we implement a function computing the output of this node, and then in the backwards pass, we compute the gradient, right? And so when we actually implement this in code, we're going to do this in exactly the same way. We can basically think about for each gate, right, if we implement a forward function and a backward function, where the backward function is computing the chain rule, then if we have our entire graph, we can just make a forward pass through the entire graph by iterating through all the nodes in the graph, all the gates. Here I'm going to use the word gate and node kind of interchangeably. We can iterate through all of these gates and just call forward on each of the gates, right? And we just want to do this in topologically sorted order, so we process all of the inputs coming into a node before we process that node. And then going backwards, we're just going to then go through all of the gates in this reverse sorted order and then call backwards on each of these gates. Okay, and so if we look at then the implementation for a particular gate, so for example, this multiply gate here, we want to implement the forward pass, right? So it gets x and y as inputs and returns the value of z. And then when we go backwards, right, we get as input dz, which is our upstream gradient, and we want to output the gradients on the inputs x and y to pass down, right? So we're going to output dx and dy. And so in this case, in this example, everything is back to the scalar case here. And so if we look at this in the forward pass, one thing that's important is that we should cache the values of the forward pass, right? Because we end up using this in the backward pass a lot of the time. So here in the forward pass, we want to cache the values of x and y, right? And in the backward pass, using the chain rule, we're going to remember, take the value of the upstream gradient and scale it by the value of the other branch, right? And so we'll keep, for dx, we'll take our value of self.y that we kept and multiply it by dz coming down. And same for dy. Okay, so if you look at a lot of deep learning frameworks and libraries, you'll see that they exactly follow this kind of modularization, right? So for example, Caffe is a popular deep learning framework, and you'll see if you go look through the Caffe source code, you'll get to some directory that says layers, and in layers, which are basically computational nodes, usually layers might be slightly more, some of these more complex computational nodes like the sigmoid that we talked about earlier, you'll see basically just a whole list of all different kinds of computational nodes, right? So you might have the sigmoid, I don't know, there might be here, there's like a convolution is one, there's and argmax is another layer. You'll have all of these layers, and if you dig into each of them, they're just exactly implementing a forward pass and a backward pass. And then all of these are called when we do forward and backward pass through the entire network that we form. And so our network is just basically going to be stacking up all of these, the different layers that we choose to use in the network. So for example, if we look at a specific one, in this case, a sigmoid layer, you'll see that in the sigmoid layer, right, we've talked about the sigmoid function. You'll see that there's a forward pass, which basically computes exactly the sigmoid expression, and then a backward pass, right, where it is taking as input something, basically a top diff, which is our upstream gradient in this case, and multiplying it by a local gradient that we compute. So in assignment 1, you'll get practice with this kind of this computational graph way of thinking, where you're going to be writing your SVM and softmax losses and taking the gradients of these. And so again, remember always you want to first step represent it as a computational graph, right? Figure out what are all the computations that you did leading up to the output, and then when it's time to do your backward pass, just take the gradient with respect to each of these intermediate variables that you've defined in your computational graph, and use the chain rule to link them all together. Okay, so summary of what we've talked about so far. When we get down to working with neural networks, these are going to be really large and complex, so it's going to be impractical to write down the gradient formula by hand for all your parameters. So in order to get these gradients, right, we talked about what we should use is backpropagation, right? And this is kind of one of the core techniques of neural networks, is basically using backpropagation to get your gradients, right? And so this is a recursive application of the chain rule, where we have this computational graph, and we start at the back and we go backwards through it to compute the gradients with respect to all of the intermediate variables, which are your inputs, your parameters, and everything else in the middle. And we've also talked about how really this implementation in this graph structure, each of these nodes is really, you can see this as implementing a forward and backwards API, right? And so in the forward pass, we want to compute the results of the operation, and we want to save any intermediate values that we might want to use later in our gradient computation. And then in the backwards pass, we apply this chain rule, and we take this upstream gradient, we chain it, multiply it with our local gradient to compute the gradient with respect to the inputs of the node, and we pass this down to the nodes that are connected next. Okay, so now, finally, we're going to talk about neural networks. Right, so really, neural networks, people draw a lot of analogies between neural networks and the brain and different types of biological inspirations. And we'll get to that in a little bit. But first, let's talk about it, just looking at it as a function, as a class of functions without all of the, without all the brain stuff. So far we've talked about, we've worked a lot with this linear score function, right? F equals W times X. And so we've been using this as a running example of a function that we want to optimize. So instead of using this single linear transformation, if we want a neural network, right, we can just, as the simplest form, just stack two of these together, right? Just a linear transformation on top of another one in order to get a two-layer neural network, right? And so what this looks like is first we have our, a matrix multiply of W1 with X, and then we get this intermediate variable, and we have this nonlinear function of a max of 0 with max with this output of this linear layer. And it's really important to have these nonlinearities in place, which we'll talk about more later, because otherwise, if you just stack linear layers on top of each other, they're just going to collapse to like a single linear function. Okay, so we have our first linear layer, and then we have this nonlinearity, right? And then on top of this, we'll add another linear layer. And then from here, finally, we can get our score function, or our output vector of scores. So basically, like more broadly speaking, neural networks are a class of functions where we have simpler functions, right, that are stacked on top of each other. And we stack them in a hierarchical way in order to make up a more complex nonlinear function. And so this is the idea of having basically multiple stages of hierarchical computation, right? And so so this is kind of the main way that we do this is by taking something like this matrix multiply, this linear layer, and we just stack multiple of these on top of each other with the nonlinear functions in between, right? And so one thing that this can help solve is if we remember back to this linear score function that we were talking about, right? Remember we discussed earlier how each row of our weight matrix W was something like a template, right? It was a template that sort of expressed, what we're looking for in the input for a specific class, right? So for example, the car template looks something like this kind of fuzzy red car, and we were looking for this in the input to compute the score for the car class, right? And we talked about one of the problems with this is that there's only one template, right? There's this red car, whereas in practice, we actually have multiple modes, right? We're looking for, a red car, there's also a yellow car, like all of these are different kinds of cars. And so what this kind of multiple layer network lets you do is now, each of this intermediate variable h, right? W1 can still be these kinds of templates. But now you have all of these scores for these templates in H, and we can have another layer on top that's combining these together, right? So it can say that actually my car class should be, connected to, we're looking for both red cars as well as yellow cars, right? Because we have this matrix W2, which is now a weighting of all of our vector in H. Okay, any questions about this? Yeah. Yeah, so there's a lot of ways. So there's a lot of different nonlinear functions that you can choose from. And we'll talk later on in a later lecture about all the different kinds of nonlinearities that you might want to use. Yeah. So W1, because it's directly connected to the input x, this is what's like really interpretable, right? Because you can formulate all of these templates. W2, so H is going to be a score of how much of each template you saw, for example, right? So it might be like you have, like I don't know, 2 for the red car and like 1 for the yellow car or something like that. Exactly. So the question is basically whether in W1 you could have both left-facing horse and right-facing horse, right? And so yeah, exactly. So now W1 can be many different kinds of templates, right? They're not, and then W2 now basically is a weighted sum of all of these templates. So now it allows you to weight together multiple templates in order to get the final score for a particular class. Right. So okay. So the question is, if our image x is like a left-facing horse, and in W1 we have a template of a left-facing horse and a right-facing horse, then what's happening, right? So what happens is, yeah. So in H you might have a really high score for your left-facing horse, kind of a lower score for your right-facing horse, and W2 is it's a weighted sum, so it's not a maximum. It's a weighted sum of these templates. But if you have either a really high score for one of these templates, or let's say you have kind of a medium score for both of these templates, all of these kinds of combinations are going to give high scores, right? And so in the end, what you're going to get is something that generally scores high when you have a horse of any kind, right? So let's say you had a front-facing horse. You might have medium values for both the left and the right templates. Yeah, question? W2 is doing the weighting. So the question is W2 doing the weighting or is H doing the weighting? H is the value, like in this example, H is the value of scores for each of your templates that you have in W1. Right. So H is like the score function, right? It's how much of each template in W1 is present, and then W2 is going to weight all of these intermediate scores to get your final score for the class. So the question is, which is a nonlinear thing? So the nonlinearity usually happens right before H. So H is the value right after the nonlinearity. So we're talking about this like intuitively as this example of like W1 is looking for has these same templates as before, and W2 is awaiting for these. In practice, it's not exactly like this, right? Because as you said, there's all these nonlinearities thrown in and so on. But it has this approximate type of interpretation to it. Yeah. So the question is H just W1x. So H is just W1 times x with the max function on top. Let me just. Okay, so we've talked about this as an example of a 2-layer neural network, and we can stack more layers of these to get deeper networks of arbitrary depth, right? So we can just do this one more time, add another max nonlinearity, and matrix multiply now by W3, and now we have a 3-layer neural network, right? And so this is where the term deep neural networks is basically coming from, right? This idea that you can stack multiple of these layers, for very deep networks. And so in homework, you'll get a practice of writing and training one of these neural networks, I think, in assignment 2. But basically, a full implementation of this using this idea of forward pass, right, and backward passes, and using chain rule to compute gradients that we've already seen. The entire implementation of a 2-layer neural network is actually really simple. It can just be done in 20 lines. And so you'll get some practice with this in assignment 2, writing out all of these parts. And okay, so now that we've sort of seen what neural networks are as a function, right? Like, we hear people talking a lot about how there's biological inspirations for neural networks. And so even though it's important to emphasize that these analogies are really loose, it's really just very loose ties, but it's still interesting to understand where some of these connections and inspirations come from. And so now I'm going to talk briefly about that. So if we think about a neuron in kind of a very simple way, this neuron here's a diagram of a neuron. We have the impulses that are carried towards each neuron, right? So we have a lot of neurons connected together. And each neuron has dendrites, right? And these are what receives the impulses that come into the neuron. And then we have a cell body, right, that basically integrates these signals coming in. And then there's a then it takes this, and after integrating all of these signals, it passes on, the impulse carries away from the cell body to downstream neurons that it's connected to, right? And it carries this away through axons. So now if we look at what we've been doing so far, right, with each computational node, you can see that this actually you can see it in kind of a similar way, right, where nodes are connected to each other in the computational graph, and we have inputs or signals x, right, coming into a neuron. And then all of these x, right, x0, x1, x2, these are combined and integrated together, right, using, for example, our weights w, right? So we do some sort of computation, right? In some of the computations we've been doing so far, something like w times x plus b, so, right, integrating all of these together. And then we have an activation function that we apply on top. We get this value of this output, and we pass it down to the connecting neurons. So if you look about this is actually, you can think about this in a very similar way, right? Like, these are what's the signals coming in are kind of connected at synapses, right? The synapse connecting the multiple neurons. The dendrites are integrating all of these. They're integrating all of this information together in the cell body, and then we have the output carried on the output later on. And so this is kind of the analogy that you can draw between them. And if you look at these activation functions, right, this is what basically takes all the inputs coming in and outputs one number that's going out later on. And we've talked about examples like sigmoid activation function, right, and different kinds of nonlinearities. And so sort of one kind of loose analogy that you can draw is that these nonlinearities can represent something sort of like the firing or spiking rate of the neurons, right? Where neurons transmit signals to connected neurons using kind of these discrete spikes, right? And so we can think of, if they're spiking very, very fast, then there's kind of a strong signal that's passed later on. And so we can think of this value after our activation function as sort of, in a sense, sort of this firing rate that we're going to pass on. And in practice, I think neuroscientists who are actually studying this say that kind of one of the nonlinearities that are most similar to the way that neurons are actually behaving is a ReLU function, which is a ReLU nonlinearity, which is something that we're going to look at more later on. But it's a function that's 0 for all negative values of input, and then it's a linear function for everything that's in kind of the positive regime. And so, we'll talk more about this activation function later on, but that's kind of, in practice, maybe the one that's most similar to how neurons are actually behaving. But it's really important to be extremely careful with making any of these sorts of brain analogies, because in practice, biological neurons are way more complex than this. There's many different kinds of biological neurons. The dendrites can perform really complex nonlinear computations. Our synapses, right, the W0s that we had earlier, or we drew this analogy, are not single weights like we had. They're actually really complex, nonlinear dynamical systems in practice. And also this idea of interpreting our activation function as a sort of rate code or firing rate is also is insufficient in practice. It's just this kind of firing rate is probably not a sufficient model of how neurons will actually communicate to downstream neurons, right? Like even as a very simple way, there's the neurons will fire at a variable rate, and this variability probably should be taken into account. And so there's all of these, it's kind of a much more complex thing than what we're dealing with. There's references, for example, this dendritic computation that you can look at if you're interested in this topic. But in practice, we can sort of see how it may resemble a neuron at this very high level, but neurons are in practice much more complicated than that. Okay, so we talked about how there's many different kinds of activation functions that could be used. There's the ReLU that I mentioned earlier. And we'll talk about all of these different kinds of activation functions in much more detail later on, choices of these activation functions that you might want to use. And so we'll also talk about different kinds of neural network architectures. So we gave the example of these fully connected neural networks, right, where each layer is this matrix multiply. And so the way we actually want to call these is we said 2-layer neural network before, and that corresponded to the fact that we have 2 of these linear layers, right, where we're doing a matrix multiply. 2 fully connected layers is what we call these. We could also call this a 1 hidden layer neural network. So instead of counting the number of matrix multiplies we're doing, counting the number of hidden layers that we have. I think it's you can use either. I think maybe 2-layer neural network is something that's a little more commonly used. And then also here for our 3-layer neural network that we have, this can also be called a 2 hidden layer neural network. And so we saw that when we're doing this type of feed forward, right, forward pass through a neural network, each of these nodes in this network is basically doing the kind of operation of the neuron that I showed earlier, right? And so what's actually happening is it's basically each hidden layer you can think of as a whole vector, right? A set of these neurons. And so by writing it out this way with these matrix multiplies to compute our neuron values, it's a way that we can efficiently evaluate this entire layer of neurons, right? So with 1 matrix multiply, we get output values of a layer of, let's say, 10 or 50 or 100 of neurons, right? And so just looking at this again, writing this all out in matrix form, matrix vector form, we have our nonlinearity here, f, that we're using in this case the sigmoid function, right? And we can take our data x, some input vector or of values, and we can apply our first matrix multiply w1 on top of this, then our nonlinearity, then a second matrix multiply to get a second hidden layer h2, and then we have our final output, right? And so this is basically all you need to be able to write a neural network. And as we saw earlier, the backward pass, you then just use backprop to compute all of those. And so that's basically all there is to kind of the main idea of what's a neural network. Okay, so just to summarize, we talked about how we can arrange neurons into these computations, right, of fully connected or linear layers. This abstraction of a layer has a nice property that we can use very efficient vectorized code to compute all of these. We also talked about how it's important to keep in mind that neural networks do have some analogy and loose inspiration from biology, but they're not really neural. I mean, this is a pretty loose analogy that we're making. And next time we'll talk about convolutional neural networks. Okay, thanks.